Hi and welcome to this Leaving Cert Higher Level Applied Maths video. In this video, we're looking at the 2025 exam paper and specifically question 7, part B. This is a projectiles question. So Chioma is throwing a basketball against a wall. The ball leaves her hands at chest height, 1.35 meters above the ground. The ball hits the wall at a height of 2 meters. Chioma is standing 3 meters from the wall when she throws the basketball with an initial speed of 6.3 meters per second at an angle of alpha to the horizontal. Calculate the two possible values of alpha. So first thing I'll always say for questions like this, it is a really good idea to do a diagram. So here is what we have. So you can see that we have Chioma here on the left. So the ball is leaving at 1.35 meters and it hits the wall at 2 meters. And then the horizontal distance between Chioma and the wall is 3 meters. So Ruth, when we talk about projectiles, we're going to just go from the point where she's thrown it. So we can ignore all of this bit underneath. So when it hits the wall here at 2 meters, what that means for us is the SY is actually going to be 0.65. So it starts at 1.35 meters and it ends at 2 meters. So it's going to be 0.65 meters above where it started. Then our 3 meters is going to be our SX, and then we're working for our alpha. So let's fill into our VUAST. I have my accelerations already in there. Remember, they're not changing. In an X direction, it's 0. In a Y direction, it's minus gravity or minus 9.8. Let's resolve first. So we're going to have 6.3 cos alpha and 6.3 sine alpha. Then our SX is 3 meters and 0.65 meters. And we're just going to let our time be t. So we have two unknowns. We have our time t and we have our alpha. So we're going to work with two equations, but that's okay because we have the x direction and the y direction. For both, we're going to use s equals ut plus a half at squared. So let's work in the x direction first. So our equation is s, which is 3, is equal to 6.3 cos alpha t plus a half times 0t squared. That's all gone. So t is equal to 3 divided by 6.3 cos alpha. So then in the y direction, we're going to have 0.65 is equal to 6.3 sine alpha t plus a half minus 9.8 t squared. And we're going to sub in that t. So 0.65 is equal to 6.3, 3 over 6.3 cos alpha. That t does simplify down, but I just haven't even bothered. If you want to simplify before going any further, you absolutely could have. But because it's going into this equation anyway, it's not going to make a big difference for us. So that's going to be squared. So that is not written very well. Let me fix it. So one of the best tips I can give when you're working with any algebra questions, and specifically where we're working with fractions, is try to get in the habits of writing these across two lines. I know sometimes students don't like to waste space, so they cram everything in. So when you cram everything in, you may have errors with reading your own. And you want to make sure that you leave a space for that over 1 for anything that's not currently part of a fraction. So you want to write anything like that 6.3 on line with the numerator. That will limit any issues that you have. I've actually lost, what have I lost there? Let me go again. So I've lost my sign. So let's try again. So sine alpha is 3 over 6.3 cos alpha minus 4.9 and then 3 over 6.3 cos alpha all to be squared. So this will make it a little bit easier to kind of work with. So you can see there's a 6.3 above and below the line there. They're going to divide into each other. We also have a sine over cos, which is going to make tan. That's from page 13 of our log tables. It's one you really need to know because we meet it quite a lot. And then we're going to do a little bit of work here. So I'm going to just focus on the numbers. So we're going to do our 4.9 or minus 4.9 by 3 squared over our 6.3 squared. And that's going to give us minus 10 over 9. and then that's going to be 1 over cos squared alpha. So going back to page 13, we're told that 1 over cos alpha is actually sec alpha. So if I square both sides, that means sec squared. And again, if you look at page 13, we have sec squared is 1 plus tan squared alpha. So it's up at the top right hand corner. So that's the substitution we're going to do. We're going to replace that 1 over cos squared with 1 plus tan squared alpha. Let's also get rid of that 9 just to make life a little bit easier. So that's going to be 5.85 is equal to 27 tan alpha minus 10, 1 plus tan squared alpha. So working that through, we get tan squared alpha minus 27 tan alpha. And then that's going to be a plus 15.85 equals 0. Now, what we actually have here is a quadratic. If you are not 100% comfortable with the quadratic, you can absolutely let tan alpha equals x. Sometimes that's actually quicker because your brain might associate that a little bit faster. So if you want to do your substitution, absolutely, I'll show you how we work it now. Sorry, let me write it up again, and I forgot my 10 at the end of that. So tan squared minus 27 tan alpha plus 15.85 equals 0. So I'm going to plug in instead of, so we're going to let tan alpha equals x. You can see what I mean. So you could have done this earlier if you're finding kind of the work with the algebraic or the work with the trigonometry pieces a little bit tricky. The rule for substitution is as soon as you can just do one substitution, that's when we can do it. So for example, we wouldn't have subbed in earlier than when we had sines and causes, we wouldn't have done it. But as soon as all we had is tans, then you can recognize that everything was kind of the same piece that could be substituted. So if we work this through with minus b, so we get first answer 1.837. And then the second answer with the minus 0.86266. 86266. That means, yeah, you go back, substitution is 1.837. So our alpha, we're going to do tan inverse. Make sure you're in degrees. We have so many changes in our exam, both maths and in applied maths. So just make sure you're very, very clear what mode you're in before you do any sine, cos, tan, or their inverses. So it's worth just always taking a glance and thinking, what am I working in? So then here we have tan alpha is 0.86266. So alpha working backwards is 40.78 degrees, or just 8 for this place. So then it says for the smaller value of alpha, calculate the velocity of the basketball as it hits the wall. So our smaller value of alpha was our 40.8 degrees. So as it hits the wall, we're basically going back to our table and we're looking for our V, where we have Vxi plus Vyj. Now here's the thing. Our Vx is going to equal to our Ux, which is going to be 6.3 cos of 40.8 degrees. So let's put that in, 6.3 cos 40.8, and it works out as 4.769. Okay, so that's going to be the I component, and they do say velocity, which means we are thinking in terms of I's and J's, which is going to give our directional piece. Once you're including some form of direction, that really is going to cover us from a vector point of view. But the easiest way to do this is just in terms of I's and J's. For the y direction, we're going to do v equals u plus at. So our v in the y direction is going to be our u, which is 6.3 sine 40.8 plus minus 9.8. And remembering our time is 3 over 6.3 cos 40.8. So you can work out the time, that's not an issue, or like here, you can go straight to just throwing the whole thing into the calculator. When you do this, we're getting a negative, and that makes actual perfect sense for us. Because think of as it's coming down to hit the wall. So the minus here means it's going in the downwards direction. So we'll 4.8. And that means minus 2.048J. So the trickiest part of that was remembering that velocity is I's and J's, and remember the speed then is the magnitude of that velocity. So we do need to see that directional piece, and again, the easiest way to show that direction is using our I's and our J's. So so then it tells us the coefficient of restitution between the basketball and the wall is 3 over 7. Part 3 then says for the smaller value of alpha, calculate the horizontal distance between the wall where the basketball lands on the ground for the first time. So let's think. So our alpha was 40.8 degrees. However, that doesn't really matter because we've already done the hard work of getting the velocity before. So the diagram on the right shows us what we're thinking about. So just going to pull this from the last part, 4.7691 I minus 2.048 J. Okay, so the diagram shows it hitting the wall at 2 meters above. Now, when we have an impact or a single body collision like this, we're only changing either the I or the J. So look at our arrows. It's coming in from the left and then it's going out back towards the left. So there's a change in the right left. That means we're only changing the I component. So this is the bit that wants to change. It's still going down, so the J component won't change. So our new velocity, so the velocity after, is going to be working with the I, putting in the coefficient of restitution. So if you want to use the formula in your log tables, we can. It just needs a slight edit. So on page 51, we have that V1 minus V2 is equal to minus E U1 minus U2, but we don't have a second particle, or you can think of it as the wall's not moving, so they're zeros. And basically we get the velocity after is minus E times U, the velocity before. So we're going to take our velocity before, which is a 4.769, and we're going to multiply that by minus 3 over 7. So we have minus 3 over 7 times 4.769, and that's going to be my I, and then the J does not change, 0.48J. So if you want to work that out, rather than leaving it there, you can do that separately. You can put it into the IJ like I did. It's just nice and neat and quick. So, and then we have by 4.769, and that's going to give me minus 2.04. I'm going to go 4 because it's 3.8. So we'll stick to 3 decimal places. Minus 2.048J. And that's the velocity right here as it's leaving the wall. So that's effectively our projectile. So now we can go to our VUAST and we can fill in everything we know. The A's don't change. It's 0 minus 9.8. We now have minus 2.044. We have minus 2.048. We know that it needs to fall by 2 meters. So that's an SY. So that's minus 2 because again, we're going down. And we want to find the horizontal distance. So this is what we're looking for. So am I red? So we're looking for SX. So again, we're kind of stuck with working with 2 points. So the easiest way to do this is we'll work in the y direction. We'll figure out our t. Once we know our t, we plug our t into the y direction and our x direction, and then we'll be able to work out Sx. So our formula that we're going to use is S is equal to ut plus a half at squared. So our S is going to be minus 2 is equal to minus 2.048 times t plus a half minus 9.8 t squared. So we're going to get two values of t here. The only one that's actually going to be valid is the positive one. So we get t is equal to 0.463. So that's 0.463 pops in there. So then to get our x directions, that was in my y direction. So then in my x direction, we're going to get s, which we don't know, is equal to u minus 2.044 times t 0.463 plus a half times 0 t squared. That's all gone. And that works out for us as Sx as minus 0.95 meters. And they want not the displacement, but the horizontal distance. So just make sure that we answer the question that we were asked. The horizontal distance, not the displacement, is 0.95 meters. So it's absolutely fine to work in terms of our vectors, but just bear in mind that we do need to answer the question that was asked.